They're like 7.
Good evening. My name is Robin Taylor, and I am president of the Philosophical Society of Washington. This is the 2,270th meeting of the Society, which is in its 139th year after its founding in 1871. We welcome our members and guests tonight for one of the enduring traditions of the Society, the 79th Joseph Henry Lecture. Tonight, we look forward to our address from our Joseph Henry lecturer, Steve Dick. Since it is a special evening, we will not read the minutes from the last meeting, but will instead allow our Joseph Henry lecturer the privilege of proceeding directly to address the Society. After the address and the question and answer period, we will have a few housekeeping announcements and then retire to the social hour and refreshments. So by way of introduction, a few brief words about our speaker. Steve Dick served as the chief historian for NASA and director of the NASA History Office from 2003 to 2009. He obtained his BS in astrophysics and MA and PhD in history and philosophy from Indiana University. He worked as an astronomer and historian of science at the U.S. Naval Observatory in Washington, D.C. for 24 years, including 3 years on a mountaintop in New Zealand before coming to NASA headquarters in 2003. He's the author of numerous books, and his most recent book is Cosmos and Culture, Cultural Evolution in a Cosmic Context. And I've shown this to you before, Steve's most recent book. Mr. Dick is the recipient of the NASA Exceptional Service Medal, the Navy Meritorious Civilian Service Medal, the NASA Group Achievement Award for his role in NASA's multidisciplinary program in astrobiology, the NASA Group Achievement Award for the book America in Space, and the 2006 Leroy E. Doggett Prize for Historical Astronomy. He is a past president of this society and is a member of the International Astronomical Union and a corresponding member of the International Academy of Astronautics. Minor Planet 6544 Stephen Dick is named in his honor. Please hold all questions until the end of Mr. Dick's lecture. And now, please help me welcome Steve Dick.
Thank you very much, Madam President. And good evening, ladies and gentlemen. I tried to convince NASA to mount a major mission to my minor planet, but so far they haven't gone. It's an honor for me to be here to deliver the Joseph Henry Lecture. As you know, Joseph Henry was the first president of the society, I think during most of the 1870s. And of course, one of the great American scientists of the 19th century. In the past, we've had Nobel Prize winners give this lecture, and I'm mindful of the fact that I have nothing in common with them except my tux. But happy to be here, and I profited greatly over the last many years from the various topics that have been discussed here, and if you are not a member, I urge you to join. Let me bring this over here. I've titled my lecture tonight, Cosmos and Culture, because of this book that recently I edited, and really there are two sides of the coin of this book, bringing cosmos to culture here on Earth, the idea being that what we know about the cosmos should affect our worldview here on Earth, the worldview of us Earthlings, the kind of thing that Carl Sagan used to talk about when he talked about the cosmic connection. And I think we really do not realize enough how the cosmos affects us. And then the flip side of that coin, which is bringing culture to cosmos. And that means using our knowledge of cultural evolution here on Earth to try to understand what other cultures might be out there. So I'm going to talk about both of those, and both of those are really huge subjects. And I'm going to confine myself mainly to the idea of life in the universe, and for two reasons. First of all, because I've written a bunch of books on that subject, but more importantly, I think nothing will affect our culture more than if we do find ET out there, or if we do not find it. Of course, extraterrestrials in popular culture, some of the greatest, most popular movies the last few decades have involved extraterrestrials, E.T. and Avatar, Men in Black, and some of you will recognize some of these novels that influenced me and influenced many scientists at NASA, and I think a lot of the general public. Arthur C. Clarke novels, Stanislaw Lem. This is Olaf Stapledon, who was back in the British philosopher back in the 1930s, who actually influenced Clarke. So there's no doubt that there's a lot of interest in this subject. People want to know the answer. And of course the answer is very hard to come by, but tonight I'm going to try and tell you how that problem is being tackled. But before we do that, I wanted to take you to Rome. Some of you may have been to this very spot in Rome, the Piazza Campo dei Fiori, the place where Giordano Bruno was burned at the stake in February of 1600, in part for his belief in an infinite number of inhabited worlds. Now, he had a few other heresies, like he didn't believe in the divinity of Christ and things like that. But anyway, he had written books on extraterrestrial life, and for all of those things, he was burned at the stake here in the Piazza Campo dei Fiori. It's now a marketplace every day. You can go and buy fruits and vegetables and that sort of thing there. And around the bottom of the statue, you'll see various scenes like this of Bruno's burning. And the entire Piazza Campo dei Fiori has become kind of a monument to the freedom of thought. Here's the Fahrenheit 451 bookstore, which looks like of course, making reference to Ray Bradbury's novel, it looks like a small bookstore, but inside you will find not only all of Giordano Bruno's books, but also it's a huge bookstore. It goes way back into there. So I highly recommend that if you go to Rome, next time you go to Rome, you spend an evening, as my wife and I, there in the forefront, always do, an evening with Giordano Bruno. So, let me set the stage for the talk tonight. The stage, of course, is the entire universe, sometimes called the new frontiers, of the infinite ocean. 13.7 billion years old, we now know, plus or minus 100 million years. It wasn't too long ago, 10 years ago, we didn't know within a billion or 2 years how old the universe was, but the WMAP spacecraft now has pinpointed it to with 100 million, plus or minus 100 million years, so 13.7 billion years old, 45 billion light years in radius. Now you might wonder why those two numbers aren't the same. The reason is 13.7, we can see 13.7 billion light years away. That's back to the beginning of the Big Bang. And we see that as it was 13.7 billion years ago, because the fastest you can get information is at the speed of light, right? Well, over the last 13.7 billion years, the universe not only has been expanding, but it's been accelerating, as we heard from Adam Rees here a few months ago. So if you were getting in a spaceship now and going to the edges of the observable universe, you would actually be going out to 45 billion light years. And everybody always wants to know, okay, what's beyond that? What's beyond that? Well, nobody knows. So how do we tackle this problem of life in the universe? In the research that I've done on this over the last, on exobiology and astrobiology over the last 50 years, I think it could be boiled down to these four disciplines: planetary science, planetary system science, origins of life, and the search for extraterrestrial intelligence. So this is how the problem has been tackled over the last 50 years. I want to say a little bit about each of those areas. Planetary science. And since I also am an historian of science, I'm going to give you at least one or two slides on each of these topics that's historical. And of course, the Copernican foundation of planetary science is the fact that Copernicus put the sun in the center, made the Earth a planet, and therefore all of the other planets might be Earth-like worlds. Everything that's been done since then, looking for life on Mars and other planets, has been to try and determine how much the other planets are like the Earth. And this is already back in the 17th century, once the Copernican theory started to become widespread. This question was asked: is there life on other worlds? Well, by the end of the 19th century, some people thought they had the answer with the canals on Mars, Percival Lowell in particular. You may not be able to see those lines there. Can anybody see the lines? Well, that's good, because other people couldn't see them really back then either. Percival Lowell said he could see them, and a lot of other people said they could see them. We now know that there's no correlation basically with the lines that Percival Lowell saw, the famous canals on Mars, which he thought were the artificial constructions of the Martians, a dying civilization that were channeling the water on their dying planet. But this controversy raged for 20 years, inspired a lot of people like Edgar Rice Burroughs. Some of you may have read these novels when you were younger. Or H.G. Wells. H.G. Wells was very much influenced by the Llewellyn Mars also. But as I say, this turned out, unfortunately, not to be the case. So why should we focus on Mars? Well, because Mars is the nearest planet for which the search for evidence of life is justified. We used to think, 50 years ago, before the space age, that Venus would be the place to search, because Venus was actually called the Earth's sister planet, very similar in size. But we now know, with the space probes, that Venus has a greenhouse effect, 900 degrees Fahrenheit, has clouds of sulfuric acid rain, very high pressures, and carbon dioxide atmosphere, not a place you would want to search for life. Mars, on the other hand, is more Earth-like, and even today there may be places on Mars that are habitable. It's a lot like the Earth, but surprisingly different. It is a rocky planet. It has an atmosphere, sort of, 6 millibars compared to almost 1,000 on the Earth. It has a hydrosphere, it has a climate. We get weather reports from Mars these days. So Mars is a natural place to look for life. And even if we don't find life, we're going to learn a lot about comparative planetology, how things develop differently on Mars than on the Earth. So the big question was in the 1960s, and this was really a driver for the American space program, is Mars dead or alive? Is there life on Mars? Mariner 4 reached Mars in 1965, and this picture was really astounding when people saw this. We forget now how astounding this was, but absolutely nobody predicted that there would be craters on Mars. You associate craters with the moon, which everybody knows is a dead planet or dead satellite, and so this was really disheartening to people who thought they might find canals or something else like that. However, only 6 years later, Mariner 9 reached Mars, and here's evidence of flowing water in the past, these dry riverbeds. And so that really renewed interest in the possibility, at least, of past life on Mars. And as I said, none of these channels here, you might call them channels on Mars, or, well, I wouldn't call them canals on Mars, but they really do not correlate with any of Percival Lowell's canals. By 1976, a few years later, we had the Viking Landers, and the results here, there were 3 biology experiments on board, but there was also a GCMS, a gas chromatograph mass spectrometer, which really trumped the other 3 biology experiments, because what that showed was that there were no organic molecules on Mars, at least at those 2 landing sites, the Viking 1 and 2 landers, down to parts per billion. So if you don't have organic molecules, it's hard to see how you have any life, because those are the building blocks for life. So this really put a damper on Mars exploration for the next 20 years. We didn't go back to Mars until the Pathfinder in 1997. But on the other hand, the Viking orbiters, the 2 Viking orbiters, did find a lot more evidence of these dry river valleys, again, for water in the past. Later, in the 1990s, the Mars Global Surveyor found gullies, and these have now been, this is a Mars MRO, Mars Reconnaissance Orbiter shot. They can really see these gullies, these things in great detail now. So it certainly looks like a liquid, and they think now water is flowing here. This one is more than 1 million years old, but over here they believe that they've caught this in the act, that there's water beneath the surface here, which every once in a while squirts out. So, and why is water important? Well, any kind of life that we know on Earth needs water. So they've been trying to, that's been the strategy on Mars, is to follow the water. And then, of course, we've had the great Mars exploration rovers, Spirit and Opportunity, which landed in 2004 at these 2 spots, Spirit over there at Gusev and Opportunity at Meridiana Planum. And these have really been astounding. They were supposed to last 90 days in early 2004. They're still going, although the Spirit is now sort of stuck in the mud, but it's rejuvenating its batteries, and may just be a stationary station for a while unless it can get unstuck. But these really have been amazing robotic ventures. They've shown us, well, first of all, in this shot, this is a great shot of Mars because you can see the polar caps. That's another reason that we know there is ice water on Mars. Most of those polar caps are ice water. Some of it's frozen carbon dioxide. So there's more evidence of water on Mars. But following the water, that strategy, this is one of the things that the Mars rovers found, which is these things called blueberries. They're not real blueberries, of course. They're hematite. And on Earth, we know that hematite is a mineral that forms only in the presence of water. So it's more evidence that there was, in the past, water on Mars. So there's plenty of evidence for past water on Mars. You have these polar caps. You have water ice below the surface, which the Mars Odyssey found. You have all of these other indications of water in the past, but no evidence for life. That's the bottom line. There's no evidence for life on Mars at present, and no evidence that there has been life on Mars in the past, except that there's been water there in the past. Now you might say, what about the Mars rock though? What about the Mars rock? 1996. I remember I was on the beach in 1996. My nephew came out and said, they found water on Mars. It just came on CNN. And I said, I don't think so. But and it's very interesting because there are Mars rocks which were blasted off the surface of Mars and intersected the Earth. These particular ones, they're mostly found in the Antarctic because you can see them against the ice pack. And after a lot of study, this particular rock, ALH 84001, which means it was the first Mars rock found down there in 1984. And after 12 years of research in 1996, NASA scientists made the claim that these objects here were microfossils or nanofossils. These are extremely small. These are much smaller than a human hair. These are scanning electron microscope images. This is probably the most studied rock in the history of the universe. And the consensus had been that this really does not show Martian fossils. I mean, when you think about it, it really would have been too good to be true, right? We're looking for life on Mars out there, and here one, a fossil lands on the Earth. Probably not. But it's caused a lot of research, a lot of discussion. And you may have read just in the last couple of weeks that the discussion is heating up again because now the same guys from Johnson Space Center and their colleagues are claiming in a different rock that they found these biomorphs, which might be mini fossils. I think it's going to, I haven't read the original research paper, so I don't know how viable this is, except there's, again, going to be a lot of discussion about this. And I think it's not likely that these are Mars fossils, but certainly going to be, you're going to hear a lot more about that in the future. So we don't have that piece of evidence either telling us that there was life in the past, but certainly following the water on Mars, and showing that there was water in the past indicates there could have been life, and so that search continues. And of course, the media will keep us up to date. We have parts of the media. They're always active, right? I just wanted to show this one because this is what we look like from the surface of Mars. This was taken with one of the Mars exploration rovers. Here we are. There we are, blown up. Everything that we do is right there. Okay, so we're still on planetary science. The other major habitat in the solar system is the ocean on Europa, one of the satellites of Jupiter. It's about the size of the moon, just a little bit smaller. We now know that these are cracks in the ice on Europa. We now know also that there's likely a liquid ocean beneath this ice. You might say, how can there be liquid way out by Jupiter? Not much sunlight or solar energy out there. The answer is because there are tidally generated energy which between Jupiter and Europa, which heats that ocean up and allows it to be liquid. And of course, where you have liquid, it could be an abode for life. So I suggest that this is really the place to say, drill, baby, drill, right down through that ice. And I think eventually we will do that. I'm not sure it'll be in my lifetime, but I'm sure that's going to be done at some point. NASA has plans on the drawing board, but doesn't have the money to do it. But that's going to be a driver. And several of the other Jovian moons, Callisto and Ganymede, it's thought, also have oceans, but it's really clinched for Europa that this is an ocean with liquid water. So that's planetary science. Now let's move to the second subject, planetary system science, the search for other planets beyond our solar system around other suns. Now we had a talk just a few weeks ago from Paul Butler, one of the major planet hunters, about this, and he talked about his work. I'm going to talk about this image in just a minute, but let me give you a little historical background first. Again, this is an idea that goes back to the 17th century with Descartes and with Fontenelle, who was a Cartesian. He had our solar system still in the center, you see, but around these other stars, there were planets going. So it's a very old idea, but how do you prove it? Well, observations are very difficult. You can't just point a telescope at a star and see a planet because it's like looking for a light bulb next to the sun. The differences in magnitude are just too great. So you can talk about theory. And the theory was that in the early 20th century was that these were this was a very rare phenomenon. It was one star passing another star and pulling out the materials to form planets. And since these close encounters were very rare, it was thought for the first 30 or 40 years of the 20th century that planets were not very common. That, however, that theory was overthrown, and by the 1950s, it was totally reversed. It was thought that planets were quite common. And in 1960, this famous piece of research, it doesn't look like much, but this made a headline in the New York Times, 1963, another solar system's found 36 trillion miles from the sun. These are very small. The idea here is that a planet around a star would have an effect on the star, right? As the star moves across the sky, any gravitational influence would make it wobble. Well, that's what Van de Kamp claimed to be measuring here. This is plus or minus a micron, a millionth of a meter on a photographic plate. And so he was claiming that Barnard's star had a planet. Unfortunately, that turned out to be spurious, and he was really 30 years ahead of his time, because it would be 1995 before the first planet was really confirmed around a solar-type star. I'll say more about that. But there were hints already in the 1980s. Here is a picture. This image actually is later, but there was this disk was known in 1984. The first observed in 1984. They put an occulting disk here, and here you see debris around the star. It was thought maybe at the time that this was a planetary system in formation. It's now known that this is actually a debris disk. The planet probably has already been formed, and this may be it. They're not sure what the mass of that is yet, whether it's planetary mass or not. But in any case, already in the 1980s, you had hints that there was material around stars that could form planets. And then in the 1990s, you had with the Hubble Space Telescope these images of what came to be called proplins, protoplanetary disks. And these really are, it's now known, these really are solar systems in formation. The planets haven't formed yet, so these are protoplanetary disks which are now making planets. But the real planets didn't come until 1995. Unfortunately, they don't look like this. This is just an artist's drawing, of course. We can't see them this close up, but this is the kind of work that Paul Butler is doing, the radio velocity work. This is, again, you might not think that this looks like much, but this might be Nobel Prize material, because this is really the first indication of a real planet. And again, instead of what Van de Kamp did, following the motion of the star across the sky, this is showing the wobble of a star as a planet tugs on it. So the scale here is the radial velocity, which means the velocity directly in the line of sight, is plus or minus 50 meters. So you can see that the velocity of the star is going plus 50, minus 50 in a nice regular sinusoid like that. So this was the first proof of a planet going around another star. That star is 51 Peg, 51 in the constellation of Pegasus, called 51 Peg B. And as Paul told us, this is extremely difficult to do, to measure at these accuracies. That's why it didn't happen until the mid-1990s, but they can now do it down to 3 meters per second. Just phenomenal, which means they can find smaller and smaller planets. So that's called the radial velocity method. Another method is photometry, which is, very easy to explain. It's just when a planet moves in front of the star, the light diminishes, right? So if you can measure diminishing of the light, then you might have a planet after you take other things into consideration. But even to measure that, you have to be able to measure 1 part in 10,000 and in the dimming of the star. So that's not easy to do either, but they can do that now. So here's a kind of an overview of the discovery of extrasolar planets. Now here's one back in 1989 that they thought might be a planet. It still might be, but they just don't know enough about it yet. Now here's a little bump in 92. These are actually planets around pulsars, which are neutron stars, very exotic stars, not solar type stars. That's why 1995 is considered the first one. Now here's another one that's a possibility. But you can see, and the numbers are up here, how many are being discovered every year, so that we now have something like 450 planets known outside of our solar system. And the color coding here has to do with the method. The blue is the radial velocity method, the sinusoid that we just saw. The green is the photometric method. The red are direct detections. So you can see the trend here, and this is only part of 2010. And you're going to see a lot more of these planets being formed. Well, what kind of planets are these? You probably can't see the axes here, but this is the mass on the vertical axis in terms of masses of Jupiter. And Jupiter is, oh gosh, Jupiter's washed out here. But it's about in here somewhere. And this is the distance from its parent star in terms of astronomical units, and this is a log scale. This is 0, so that means that the Earth is right about here. So you can see that there have not been any planets found that are the size of the Earth yet. And the other big surprise is that most of them are very close to their star. In fact, most of these are gas giants, even bigger than Jupiter. And here you can see 478 of the nearby planets that how close these are. Some of these are closer than Mercury to their parent star. And you can also see from this that there are some systems that have been detected, but for the most part, only one big planet has been detected around some of these stars, probably meaning that we haven't found the other ones yet because they're too small. Now, here's an amazing image from the Hubble Space Telescope. And again, this is a debris disk. And this was first imaged in 2004 around the star Fomalhaut. And a few years later, they imaged it again. And here you can see that little dot blown up here. It has moved from 2004 to 2006. This is a planet, a direct image of a planet. So these are very difficult to image, but this is truly an amazing image, one of the many that Hubble has done. So we can now begin to directly image some of these big planets. Now, Kepler, of course, is the big thing now. Kepler is the mission, the NASA mission, to observe Earth-sized planets, monitor 100,000 stars using this photometric method of planets transiting in front of the star and measuring the diminution in the light down to 1 part in 10,000. Kepler's first results were just announced at the American Astronomical Society meeting last January. And here you see the first 5 planets announced. Kepler 4b is the smallest one. And you can see it's quite a bit bigger than the Earth. It's 4 times the diameter of the Earth, as a matter of fact. Kepler 7b is another interesting one. This is called a styrofoam planet because it's 1/10 as dense as Jupiter. So what's going on there? You know, we don't know. A styrofoam planet. Maybe there's a lot of aliens using styrofoam cups and trash and all that. But you're going to see a real flood of these over the next few years. Hundreds and hundreds, maybe thousands of planets found. It's a huge job. Kepler's only going to look at this little part of the sky. Here's the galaxy. So that gives you some idea of what the job is to find these things. Okay, so before I go to that, so the bottom line here is that more than 400 planets have now been found outside of our solar system. None of them are Earth-sized or Earth-like as far as we know yet. Most of them are gas giants, but in the future we're going to hear a lot more about these and find the smaller ones, which of course are more difficult to find. Okay, the third area is origins of life research. I'll talk about this image in just a minute. This is a hydrothermal vent under the ocean. But the big picture here is the question, is life just a sideshow or is it a cosmic imperative? Well, it depends who you talk to. Here's a famous book done, probably 10 years ago now, called Rare Earth: Why Complex Life is Uncommon in the Universe by Ward and Brownlee, an astronomer and a geochemist. And they concluded that microbial life might be very common, but that intelligent life was very rare. Of course, it depends how you define rare, too. On the other hand, here you have Christian Deneuve, who is a Nobel Prize winner, who says that life is a cosmic imperative. Basically, wherever you can have life, life does develop. So it really hinges on, even if you find planets that are like the Earth, it really hinges on how common is the origin of life. Is it a cosmic imperative or not? Well, what do we know about the origins of life on Earth? Happened probably, well, we know, 3.5 to 4 billion years ago. Where? The oldest certain evidence is 3.5 billion years ago in Australia, these microbial mats known as stromatolites. But the big question is, how did it happen? And there's been a lot of work done on that, but no definitive answer. This more than 50 years ago now, this famous experiment where Stanley Miller put methane, ammonia, water, and hydrogen in a reducing atmosphere, a presumed primitive Earth atmosphere, into a flask, gave it a spark discharge, and lo and behold, you got amino acids out. Now, amino acids aren't life, but they're pretty complex organic molecules in the building blocks of life. And so this was thought to be the beginning of something big, but lots of experiments have been done since then, and there's not been a whole lot of progress. So, and of course, organic molecules are a long way from life. So that has sort of reached a dead end. And moreover, it's now thought that the primitive Earth atmosphere may not have been composed of this anyway. So it's even more uncertain. But there's been a lot of new research on the origins of life. First of all, here are these hydrothermal vents, these black smokers, located at the bottom of the oceans, at the places where seafloor spreading takes place, where the tectonic plates are spreading, and where these mineral-rich fluids are coming out from the crust. And this is hydrogen sulfide. And what do you find? Lo and behold, you find life at these tremendous depths, pressures, and temperatures. And not only primitive life, but these tuberums, which can be up to 3 or 4 feet long. I'm particularly interested in this because one of my sons goes down to the Alban to look at these things. And I always tell him, don't tell us until you get back, because this is like, I don't know, 8,000 feet down or something like that. So, but anyway, there's a lot of research going on in these areas where you have this seafloor spreading. And so the bottom line here is that not only with hydrothermal vents, but with lots of other things, with extremely acidic environments, with extremely salty environments, even with extreme radiation, the radiochar, I think it's called, microbes, that life can flourish in extreme environments. Now, that doesn't mean that there's life out there in outer space somewhere. It means that the conditions are, the conditions under which life might flourish are more than we thought in the past. So there still is not any proof of life, and certainly not proof of a cosmic imperative. Moreover, we have found complex organic molecules all over in outer space in these giant molecular clouds, all kinds of organic molecules, including amino acids. But again, amino acids is not life, so the big question is, is it eventually delivered to planets in ways like this? Delivered from comets or delivered from meteor impacts, is that not really much of a factor? So nobody knows the answer to that question yet. I think one of the big things in the future is going to be biosignatures, looking at atmospheres of planets. And the Hubble Space Telescope actually has done 1 or 2 of these, but you really need a telescope dedicated to this, where you can determine what's in the atmosphere of these planets that they're finding. And this is going to be, I think this will be one of the big trends in the future. So the bottom line on origins of life is that we just don't know if life is a cosmic imperative or not. So you can begin to see the pattern here, that there are a lot of things that we don't know, and there's no proof that there's life out there, a lot of sort of circumstantial evidence. And then we come finally to the search for extraterrestrial intelligence, the fourth sort of pillar of this whole endeavor of astrobiology. This is actually an image, a beautiful image from Hubble Space Telescope recently, right after the new camera was put in. Each one of these is a star. And so, you know, one of the most powerful arguments for intelligent life out there is when you go out and look up in the sky and you've got all these stars up there and you say, surely we can't be the only ones, right? Well, we could be. But that's a powerful kind of argument. And other people have said it'd be an awful waste if we were the only ones in all of this space. But that's, of course, no proof. This also has a long history, the search for extraterrestrial intelligence by radio, even Marconi. Here's Marconi, New York Times, 1920, front page, I think. Inventor says waves of ether are eternal through each other planets. Get strange signals now. These, he declares, might conceal they proceeded from other worlds. So almost as soon as you had radio, people were thinking about how you might signal and how you might communicate. Here's another article along the same lines. And then we come to modern SETI, Frank Drake. This year, in fact, just last month, we celebrated the 50th anniversary of Project Ozma, which was the first radio search for extraterrestrial intelligence. You see here the famous Drake equation, which I'll talk about in a minute. Drake is still very much alive and in good health. In fact, we're having a meeting at Green Bank where his original observations took place. We're having a meeting down there in the fall where we're going to talk about new possibilities for SETI, new ways of looking for extraterrestrial signals. But here's that Drake equation, the subject of a lot of ridicule by some people, because what N is here is the number of technological civilizations in the galaxy. Drake came up with this equation all the way back in 1961, shortly after his first search. And he just was putting on the blackboard what would be the factors, you know, if we're going to look for extraterrestrial intelligence, how many civilizations are out there? Well, what are the factors? So he started writing them down, the rate of star formation, the number of stars that have planets, the number of planets that have an environment conducive to life, the number in which life actually develops, the number in which intelligence develops, the number in which technological civilizations develop, and the lifetime of a technological civilization. Because if you have civilizations that last 1 million years, you're going to have a lot more of them around than if they die off after 100 years, right? The problem with this is that aside from this value, the rate of star formation, and now this value, which we're starting to get from the planets that we're finding, we have no idea what these other ones are. So everybody plugs in their own favorite numbers. Drake gets maybe 1 million technological civilizations in the galaxy. Some people get 1, which is us. Some people get, I always tell them that you have to be careful, they're going to prove that we don't exist. But this is, you know, Drake never meant it to be an equation like F equals ma. It's just sort of a heuristic device whereby you can talk about what the various factors are for the development of civilizations. And you can break it down into astronomical evolution, biological evolution, and over here, cultural evolution. Of course, nobody knows what the lifetime of a technological civilization is. If you define technological civilization as a radio communicative one, we're about 100 years old. Or if you define it as a computer technological civilization, it's even less than that. So L is one of the big uncertainties in this equation. There are various SETI programs going on, but there are also lots of problems. You saw all those stars out there. Where do you look? Well, you start by looking around solar-type stars. And in fact, you can now start to look where are their planets. We know there are planets. Another problem is what frequency, because basically you've got a radio dial here of billions of frequencies. What channel do you tune to? And people came up with all kinds of sort of magic frequencies that you might use, and then got around this somewhat by being able to scan frequencies, millions of frequencies at a time. But it's still a problem because there are so many frequencies to look at. A more fundamental problem is, why would any civilization be aiming a message at us? You know, unless you're unless you have an isotropic beam which is going out in all directions, which is very expensive. We don't know about extraterrestrial economies. But why would they be aiming a beacon at us? They wouldn't know that we're here because, if you think about it, the radio, we've had radio for less than 100 years, or TV for, what, 50 or 60. If a civilization is located 100 light years away, they wouldn't even have gotten our earliest TV signals yet, so they wouldn't know to aim anything back at us, right? So that's a kind of a fundamental problem. Why would any civilization be aiming a beacon at us? Why should, and if we're doing SETI, if we're listening for these, why would we think we would find them? And then another problem is, would they use radio? Would they use radio waves? There are certainly reasons to think they would use radio waves. But on the other hand, there are fewer and fewer radio waves bouncing around from the Earth since we're going from broadcast to cable these days. So maybe they've, maybe they've gone to cable a long time ago. So there are lots of fundamental kinds of problems with this that have been discussed in considerable detail, and we'll be discussing again. Now, here's one of the fun things, though. Back in the 1970s, the famous Fermi Paradox, named after Fermi, who first raised this in the lunch discussion, just simply, where are they? Where is everybody? So here are just some of this book I think came up with, 50 solutions to the Fermi Paradox. The idea being that if you take into account the time scales of the universe, you heard me say that it's 13.7 billion years old. Well, it would take a while for civilizations to form, stars to form, planets to form, civilizations to form, but they could be billions of years older than us. It turns out that if you have, and somebody did this calculation back in the 70s, if you have a civilization that's interested in interstellar travel, they would have covered the entire galaxy in a few million years. So in that case, why don't we see them? They should be here. Where is everybody? Here are a few of the answers. They are here. UFOs, some people think. I'll say a little more about that later. The Zoo hypothesis, they're waiting for us to get smarter. They're just out there watching. Interstellar travel is impossible. Maybe, but that's a little hard to believe when you're a million-year-old civilization and haven't figured it out. They're not interested in us. This gets into extraterrestrial sociology. Maybe they just don't. They're not very sociable, They're not interested. This is my favorite one. Lack of funding, gridlock in the extraterrestrial Congress. Or they don't exist. This is a very serious objection. When you think on timescales, which you have to do, think on timescales of the timescales of the universe in terms of millions or billions of years. That they really ought to be here. We should have seen them. So just to summarize these four areas, I haven't talked about all of these things, but this is what has given rise to the science of astrobiology. It used to be called exobiology. It's quite a robust science now, with NASA spending something like $50 million a year on it, which of course is just a small amount compared to most of its mission. But it funds a lot of research in these various institutions, universities and other institutions. And the bottom line is that we still do not know the answer. But this is the approaches that are being, these are the approaches that are being taken. Okay, some challenging questions, lots of challenging questions, and I'll give my own personal answers to some of these because there's no definitive answer. I guess mine's as good as anybody else's. So, what about UFOs? Well, 95% of them are explainable. I have a whole chapter on this in one of my books. How about the rest? In other words, if 95% are explainable, what do you do with the other 5%? Do you say, well, those are, if you can explain 95%, probably there's some explanation for the other 5%. Or do you say, that's the 5% that you really want to look at? I sort of tend toward the latter one, that we really ought to look more closely at that 5%. But there's no government agency that looks at this, and no serious scientific study of that really. And what it comes down to is I think that it's not likely that they're extraterrestrial spacecraft, but it could be some other interesting phenomena, some psychosocial phenomena. And what it really comes down to is the nature of evidence. And I always like Carl Sagan's quote that extraordinary claims require extraordinary evidence. Some people think that there may be evidence of UFOs, but I don't think that anybody can claim that there's been extraordinary evidence. they didn't land on the White House lawn, or there aren't any really good pictures and that sort of thing. So, I think the 5% deserves more study, but very likely not extraterrestrial in origin. And here's one that's been hot in the last few weeks. Should we communicate? Stephen Hawking, said no. They might be bad guys out there who might come to get us. So this is what's called SETI versus METI, the search versus messaging ETI. It's one thing to sit here passively and search. It's another thing to actively send a message out. That's been done a couple of times. Once back in the 70s when Frank Drake did it from the Arecibo, sent it to a globular cluster, which is one of these huge clusters of stars with a few 100,000 stars in. Unfortunately, it's 25,000 light years away, so we wouldn't hear an answer for 50,000 years. But the question is raised whether we should be doing that, whether we should be revealing our position. And some people point out that, of course, that TV signals have been going out anyway. But although the carrier signal may be detected, the program content probably, luckily, is not decipherable. And in any case, this was also raised back in the 1970s by actually a Nobel Prize winner, astronomer Sir Martin Ryle, who's had basically the same position as Hawking. And I remember the New York Times had an editorial the next day entitled, "Should Mankind Hide?" And that's sort of what it comes down to. Are we going to cower here on Earth afraid that the extraterrestrials are going to come and get us? I don't think we should do that. On the other hand, it's a real question if they are good guys or bad guys. There's no way to know. Who speaks for the Earth? There are the International Academy of Astronautics. I'm actually on one of the SETI committee that talks about these things. Who speaks for Earth? What do we say? And there are lots of arguments back and forth whether we should do any active SETI at all, in the sense of sending any message out. I mean, people really get in, serious arguments about this sort of thing. So this is one of the big questions. I think, who speaks for Earth is one of the big questions, and I think that's an entirely open question that still has to be determined. I don't know who should speak for Earth. Whether or not we want to contact them depends to some extent on what they're like. There are two possibilities. They're good guys who will teach us all the knowledge and wisdom of the universe, or they're bad guys. H.G. Wells here. That's the classic version. Here's the modern version. Good E.T. or bad aliens. So which one is it? We have no idea whatsoever. But I had proposed in an article that I did a number of years ago that if we're going to try to understand the nature of intelligence, that we need to think on long time scales, cosmic time scales. These kinds of time scales, remember, cosmic evolution is 13.7 billion years. After you take into account the formation of stars and galaxies, and then it took 5 billion years, 4.5 billion years on the Earth for intelligence to form. There could be civilizations out there that are billions of years old, right? So I proposed, and this is one of the articles you'll find in this Cosmos and Culture volume. It's actually reprinted from a number of years ago. I proposed that the extraterrestrials might actually be postbiological. Because if you take cosmic evolution seriously, we know that there's astronomical evolution, we know that there's biological evolution. You have to take cultural evolution into account. On planet Earth, 10,000 years ago, biologically, we weren't very different. We sure are different now culturally than we were 10,000 years ago. So the dominating piece of cultural evolution really is cultural evolution. So if you have extraterrestrials several billion years old, they don't really need to be several billion years old. If you think of lifetimes of technological civilization in terms of computer technology and ability to do artificial intelligence, in the long term, I think cultural evolution would produce something far beyond biology. And I explained all this in detail, fully referenced in the article, in terms of any civilization that can improve its intelligence, would improve its intelligence, And of course, this depends on artificial intelligence, the strong AI interpretation. You can get a lot of interesting arguments on this. But here's, this is the conclusion that I came to, that we ought to contemplate, think about at least, the fact that cultural evolution has resulted in a post-biological universe, and that this would have implications for SETI strategy. That if you're looking for, if you're communicating with a machine or artificial intelligence, you might want to have some different ideas than if you're communicating with what we think are people like us. I think almost certainly you can say that they're not like us. This was a popular version of the article. To put it on the cover, they aren't who you think. Extraterrestrials may have more in common with your computer than with you. This actually has raised quite a bit of discussion, and I think we'll probably discuss it down in Green Bank in the fall too. What would your strategy? How would your strategy differ if you're looking for post-biological intelligence rather than biological? Okay, just a few words. I know I'm coming to the end here. One of the implications of discovery of extraterrestrial life, a very interesting discussion, very complicated discussion once you start to break it down, because of course it depends on the scenario. If microbial life is found, it's quite a different reaction than if intelligent life is found. If it lands in the White House lawn, it's quite different than if it's found a million light years away, right? If they're good guys, it might be quite different than if they're bad guys. So once you start to break all these things down, you can really get a lot of interesting discussions. It would vary in different cultures. It would affect religious doctrines in different ways. And there's a long history of discussion of this with Christianity and other religions. And of course, it would determine our place in the universe, whether we're the only ones or whether we're going to be interacting with extraterrestrial intelligence. Here are some of the meetings, and I've gone to all these meetings going back to the early 90s about the implications of astrobiology. Just before NASA launched its SETI program on the 500th anniversary, the quincentennial of Columbus's landing, we had the observations begin both in California and simultaneously at Arecibo. Just before all that, we had this workshop on the cultural aspects. That's what SETI is. Cultural aspects of SETI, which resulted in this publication. There were workshops on the societal implications of astrobiology out at NASA Ames in '99. The Templeton Foundation has had a meeting on this, and I've edited a volume on that subject. Foundation for the Future, located out in Washington State. The AAAS program, the Dozier program, Dialogue Between Science and Religion, has also done a series of workshops that were actually funded both by NASA and by the Templeton Foundation. And if you want to, I don't have time to go into this, you can ask questions afterwards if you want, but I would suggest that you look at either one of these two books. This is that one that I edited from the Templeton meeting a number of years ago, The New Universe, Extraterrestrial Life, the Theological Implications. Lots of interesting articles from the director of the Vatican Observatory, a wide range of theologians, scientific types, and other people. This one is more recent, by Connie Burke. This just came out from Cambridge, and the subtitle being Philosophical, Ethical, and Theological Perspectives. So quite a bit of thought has been given to this idea of what the implications might be. And I think it's a good idea that you don't wait until you know for sure, or they show up, that you start to think about these things, ahead of time. Okay, one final question before I end here. Why is the universe fine-tuned for life? Why are we here? Why is the universe in such a way, with such properties, that we can exist at all? This is the so-called anthropic cosmological principle, which really goes all the way back to the 1960s, but really picked up in the 1980s there. The realization that evolution is strongly dependent on the global structure of the universe, truly surprising and no less remarkable than the universe itself. And I won't have time to go over all this, but if you get a chance, if you want to read about this, Martin Rees's book, Just 6 Numbers. If any of these 6 numbers were different, as these parameters of the universe, life would not be able to exist, because planets wouldn't be able to exist, or stars would not live long enough for that sort of thing. The force of gravity was much different, we wouldn't exist. If the binding power of the nuclei, the weak nuclear force was different, the elements for life couldn't exist. The expansion, if the expansion was too slow, no galaxies and stars, if too fast, it would have collapsed a long time ago. The accelerating universe also comes into this, and all these others too. So the universe seems to be just right, a Goldilocks universe, just right for life. And the question is, why is that? Well, here are some explanations that have been offered for the biofriendly universe. A famous God hypothesis, you may have heard of that one, that has a long history of design, the design argument. A highly evolved natural intelligence, fine-tuned the universe. That's an interesting one. A multiverse exists, an ensemble of universes, and we happen to live in one suitable for life. Or it's all just a coincidence. What do I mean by the multiverse? This is how the multiverse was recently defined. The possibility that there are other universes in which the constants of physics and maybe the laws of nature are different. And here I like these 4 levels of multiverse that the physicist Max Tegmark gives. Universes in terms of beyond our observable horizon. There could be many big bangs, and we're just one of the big bangs. The many worlds of quantum physics, which says that every possibility becomes a reality. And then these mathematical, the idea of sort of platonic mathematical structures. So is this science? A lot of people think it's very doubtful whether this anthropic principle is science. Here's Heinz Pagels, who was the husband of Elaine Pagels. Some of you may know Elaine Pagels, who is the theologian or biblical scholar at Princeton. He said that it's been sterile. It's not science, needless clutter. Bernard Carr, who did a huge 600-page book on the multiverse, sort of says the same thing in this because you're not able to observe these other universes, so it's not really science. On the other hand, he turns around and says there's been a fundamental change in the epistemological status because of the many ways in which we now realize the universe could originate. Some of these ones that I just showed you. So, why is the universe biofriendly? God hypothesis, unverifiable. Multi-universe, unverifiable. Highly evolved natural intelligence may be verifiable in principle, but very difficult. This has been proposed by famous people like Trent Hoyle and James Gardner in his book Biocosm. I even talked about it a little bit in my article I did called Cosmotheology. And I think it's good to remember Sherlock Holmes here. You've all heard this quote. Whenever you eliminate the impossible, whatever remains, however improbable, must be the truth. Or it's a coincidence. So, and I like this sort of closing quote from Freeman Dyson, who was at our meeting, a Temple meeting in that, and is represented in that volume that I edited. He says that the prospects are bright for a future-oriented science joining together in disciplined fashion the resources of biology and cosmology. Now, he said this 20 years ago, more than 20 years ago now. It hasn't happened yet. But the problem is that in a disciplined fashion, I think when that does happen, that fine-tuning in the multiverse might be important parts of that discussion. So, just to conclude, the possible outcomes of cosmic evolution: physical universe, biological universe, post-biological universe. In a physical universe, cosmic evolution ends with planets, stars, and galaxies. We're just a fluke. In a biological universe, life is common, and we can join that galactic club. That's quite a different universe. Or in a post-biological universe, cultural evolution has replaced carbon-based intelligence with artificial intelligence. Our future is written in the stars. It's already happened out there. Some people think we may become post-biologicals in the not-too-distant future. So maybe that will give you some food for thought, enough food for thought for one evening. And if you want to learn more about some of the things I've talked about, I'd suggest these 3 books here. Thank you very much.
Take some questions. It's a little hard to hear in this room, so if you have a question, if you would stand when speaking your question, and please try to speak up.
Ron?
Yes. When I was young, if I remember correctly, the whole idea of considered among scientists to be kind of a disrespectable idea.
Yep.
And here it is, you know, and it's utterly changed, which brings the question to mind, the culture that we live in. How has that changed? How has the culture of scientists changed that made that happen? And do you think that the study of UFOs might also return to respectability for some reason, perhaps related to that?
Repeat the question.
What does, back in the, 40 or 50 years ago, this was not a very respectable subject. Now it is respectable. Why is it respectable? Is it because our culture has changed? Certainly, our culture has changed. I think that one of the big changes is that we're able to study it a lot more now. I mean, back, 50 years ago, before the space age, you couldn't study the details of life on Mars. We couldn't find the extrasolar planets. There wasn't much known about the origin of life. You couldn't do SETI yet because there weren't radio telescopes, or at least not very big ones. So, and I remember, I actually did my dissertation in the 1970s on the history of this debate in the History of Science department. And when I proposed to do this in the History of Science department, they said, well, there are two problems. First of all, it's not science. And secondly, there's no history worth writing about. But, so it certainly was not respectable in academia then, but actually, they let me do it anyways. And the dissertation was published. But, so I think the science, what we know about science now, what we know about these relevant areas that I've talked about is a lot greater now, so that it's more amenable to scientific study. My tendency would be that UFOs will not have that same fate, just because the evidence, I don't see how you can study, what tools would you have that would give you a better handle on the UFO, the whole UFO phenomenon? I don't know. Yes?
I think there's another aspect to this cultural phenomenon.
Right?
And you touched upon it in the very beginning of your lecture when you talked about your son going down into the Alvin and showing the tube worms and all the fantastic creatures that exist down there
Right.
in the sulfur-driven biology, the sulfur-driven life.
Yep.
And I find it interesting that young people coming into our physics department are all kind of looking outwards. But I think it was Stephen Jay Gould coined the phrase "strangers amongst us," and I'm culturally surprised, being someone who works at the nexus of physical body. I'm surprised why there isn't more interest in the kind of discoveries that are being made in the Alvin, or the new discovery of the deepest hydrothermal vent, which was just discovered in the Caribbean. And here we're looking at hemoglobin, elementary forms of hemoglobin, which exist in the tube worms, and elementary rhodopsins, which exist in shrimp in dark areas and have no sense of light. So can you answer that question, why the interest is so intense about going off the planet, but to me, it isn't matched by the intensity of interest in looking at our own planet and at these strangers amongst us?
Yeah, great question. I'm sure there are many factors, as usual, many factors. For one thing, there's not a lot of science fiction about the ocean, or the hydrothermal vents, so people aren't sort of inspired from that angle. Everybody can look up and see the sky and wonder why.
That's probably it.
Why there's so, why, if there are extraterrestrials out there, whereas not everybody even sees the ocean.
That's it.
So, yeah, I think it has to do with that, and it's a lot of it's more sort of common sense than studying the details of hydrothermal vents. Not much of the public even knows about hydrothermal vents, whereas everybody knows about the possibility of life on other worlds. So I think there are a lot of different things. That's a good question, though. Yes, sir.
It seemed like your whole talk was about animal life.
Right.
What about plant life? You spoke of the one experiment that generated amino acids. Is there a similar experiment that would generate something needed for plant life? And what about mechanical life? It seems like, you know, it's very unusual that all the parts of a human got put together, so we have this now. But what about maybe all the parts of steel and iron and dirt and everything else could make a machine that reproduces?
Well, I think for the origin of life debate, we're not talking at the level of animals or plants. We're talking at the level of, you know, the most primitive life, microbes and below. So it's not really, you don't really talk about the origin of animals unless you're talking about a lot further down, in history, or the origin of plants. You're really talking about the origin of life. We're talking about extremely primitive life.
Well, extremely primitive plant life I would include in that.
First, we should define the life.
What's that?
First, we should define the life. What
Yes.
is life?
Well, the whole question of defining life is an interesting one. I was saying earlier that there's a famous article on the meaninglessness of the term life, because it's very difficult once you try and define life. And this is a practical question. You know, when they send the Vikings to Mars, Viking Landers to Mars, they sort of had to define life, you know, because they had to design their experiments around what they expected to see. Well, maybe life is something that they don't expect to see, and that's why some people think that wasn't those experiments weren't very well defined. Although it's hard to argue with the lack of organic molecules from the mass spectrometer. So, yeah, yes, sir.
How are the real estate values holding up on some of these Seriously though, but I want to, this lady asked a good question and the gentleman after her, and I want to kind of continue with that.
Okay.
Okay. Theoretically, I mean, we believe now that the stuff that we are came from the ocean, so to speak, and that our evolution got out of the ocean and got onto the surface more. So my question is, considering that the conditions of other planets or whatever are going to be very much different than ours, the environment in which anything would exist is going to be a different environment. Isn't it likely that some of the evolution of stuff would be more underground and that the surface would be more a protector of barrier? For example, we have the inner core, which generates a tremendous amount of heat for our planet, where we use the sun from the outside. But other places might have the stuff more packed in, where they will develop under the surface, and the surface would be their protector, their barrier cells.
Well, yeah, that's a good question too. And in fact, on the Earth, one of the forms of extremophile is the very deep biosphere. They found these things, I forget how far it is, miles below the Earth, microbes miles below the Earth. You know, the hydrothermal vents are not photosynthetic, they're chemosynthetic. So yeah, you have to consider all kinds of different possible metabolisms. And in fact, on Mars, a lot of scientists think that under the soil is where you might find the life. You know, and the skeptics say, okay, they haven't found any on the surface, and so now they're going to look for it in more exotic places. And you know, some of the skeptics don't think that's very good. But yeah, I think you have to really think. One of the great things about this debate is you really have to think in very general terms. You have to get outside the box. Somebody once said to me, when you're going to think outside the box, it's good to know what's in the box first. But you really have to think in a sort of generalized way that you don't normally. And that's one of the reasons that, you know, over the last 30 years, this has kept me interested, because in this debate, you can talk about anything ranging from astronomy to biology, chemistry, and theology and philosophy. And there's just, it's just so interesting from so many different points of view.
Yes, I've enjoyed this very much. I think the Cosmos Club is a great place to have this particular lecture.
Cosmos, yes.
Yes, and you talked about the accelerating universe and the technological or cultural evolution succeeding biological evolution. 50 years ago, America was a third world country compared to what it is now. And we have, my grandfather died in the 50s and was amazed at the technological progress that he had experienced in his own life. And he died before Sputnik. We've had a lot of progress since, and Ray Kurzweil, in his book, The Singularity is Near, claims that the evolution, technological evolution is accelerating because the better your technology, the better you can increase the technology. And that in another 30 years we'll reach what's basically an asymptote. It'll be basically straight up as far as we can go. How will this affect our view of what other civilizations might produce? How will it affect what we can do? And will we indeed in 10 years have 20/20 hindsight?
Well, that's one of the reasons that I like this idea of a post-biological universe. Of course, the weakest part about the idea of a post-biological universe is probably that it's not bold enough. Because what it is really is an extrapolation from what we think might be happening on the Earth now. For example, Kurzweil, which a lot of people think is far out. And by the way, when you talk about humans becoming post-biologicals, you get a lot of reaction from people who think, that really would not be a good idea to abandon humans and become machines. A lot of interesting discussion there. But I think our conceptions of extraterrestrials are based on what's happening in our contemporary culture. And that's why, post-biological, for example, is just an extrapolation. And I don't know what else to say about it except that we're bound to view the universe in different ways as, it's all an embedded part of our culture. Okay, one more? All right, you. Yeah, go ahead.
All right. I'm wondering if you have any ideas on what sort of messages we could send out. Stuff like the Voyager Golden Records. Is that the best sort of idea that we could send?
Probably not.
Encoded communication.
Yeah. There actually have been some messages sent out. I mentioned the radio message sent out by Frank Drake, and the Pioneer plaques. The Pioneer plaques had a message on, and then the Voyager records. Looking back on those, they really seem very primitive, and in fact, most people on Earth can't figure out what some of them were trying to say. so it's very difficult to come up with what you would want to say, or more to the point, what they would be able to understand out there. And I think this has been the great flaw in the SETI program, is trying to project ourselves out to the extraterrestrials, to think that they're going to be like us. And it's entirely possible that we won't be able to communicate at all. That our brain structures are totally different from their brain structures, and there's no way to communicate. And if you ever read any Stanislaw Lem, Solaris, communicating with the ocean on Solaris, that's a good place to start for that in thinking about how difficult it might be to communicate. On the other hand, I don't fault Frank Drake and others for doing what they can with their thing. They have radio telescopes, and it's possible that that might be one way that communication could take place. And it's possible, I guess, that out of all the civilizations out there, there might be a few that are similar to us or at our stage of development. But there are a lot of other different possibilities too. So I don't know what I would say. I'll have to think about it. Okay. Thank you.
Appreciation. I'd like to present you with this framed plaque, which is a framed copy of your announcement of the lecture tonight, which is signed by all the members of the General Committee and those who attended your dinner tonight. Thank you very much.
Thank you very much. And if anybody would like to take a look at this book, I'll leave it here and have a look. Okay, thank you all for coming. Thank you.
and have not yet settled your account, if you would see our treasurer, John Ingersoll, who is, there he is, if you would see John before you depart tonight. And if you're not a member of the society, and if you are interested in joining us, receiving invitations to dinner with the speaker and announcements of upcoming lectures, if you would see our membership chairman, Eric Gottschall, who is in the back, and he has a membership application for you. We would welcome your membership in the society. Finally, this is the last meeting of our spring semester. Our next meeting, the 2271st meeting, is on September 10th, 2010. Our speaker will be Hod Lipson. He is a professor of computing and information science and mechanical and aerospace engineering at Cornell University. His lecture is entitled, "The Limits of Science, Can Scientific Discovery Be Automated?" And I understand he is an excellent speaker, so please join us. I will now accept a motion for adjournment of the 2270th meeting. Second. All in favor? All opposed?